So, Chapter 17 assignments are currently due tonight. How do you guys feel about that? There's a lot of reports that 17 is going better than 16, and I can see why. Capacitors are weird, frankly, among other things.
I have like a question on 8, but like G and H. Like I understand what the other ones are asking and with like what stays the same and what changes according to like series and parallel. But then like G and H. Well, I know that H uses G, so I couldn't get G.
Oh. In cases like that, you can always, as a general rule, please email me so that I can make sure you're on the right track before you just spend all your attempts getting part 1 right and then can't do part 3.
I got it on my last attempt, but like at that point I was just like,
I'm going with that.
I actually did feel bad.
That sleep is important.
It was like 10, so.
8, that's the combo circuit, correct?
Mhm.
Oh, longer than I thought it was. Oh, I was thinking of 7. Okay. So, part 8 is a combo circuit. First thing to do is find the total resistance of the entire circuit. Actually, the first couple of parts step you through finding the resistance of the entire circuit. Then we get to the current through the battery, therefore the entire circuit is part E, and then we have part F. What is which part was your question about?
G.
G, okay. So F is potential drop difference across the first part. Using the result of part F and 3 ohms. Okay. So, in this combo circuit, going towards A through F, we've stepped through finding the total resistance, the total current, and we've started looking at some of the things that happen to each individual resistor. So, use the total resistance with the total voltage to find the total current. The total current is the answer to part E, I believe. Yes, so E is the total current that travels throughout the entire circuit. That total current is going to come out of the plus, travel through R2. So R2 is going to get all of that current that you just found. That's going to give R2 a specific voltage drop. If we use that current with R2's resistance to find its voltage drop, that will be the answer to part F. Then we get to here. At this point, the current is going to split. Some of it's going to go here, some of it's going to go down the rest of this pathway. Now, the question isn't asking necessarily about how the current is going to split. What we are asked for part G is what is the magnitude of the voltage drop across the 3 ohm resistor. And everyone's going to have the same, it's going to be the same one on everyone's page, because that's part of the image. And, pardon me, every circuit, every problem will tell you your own specific voltage for the entire circuit. This one's 7.5, and everyone will have a different answer for part F, the voltage drop across that first resistor. So in this particular case, of the 7.5 volts in the circuit, 2.62 of that 7.5 has been used up, pushing the current.
Resistor 2?
Correct. So now we have less voltage left. We've spent some of it getting the current through R2. And the difference between this number and that other answer is the amount of voltage remaining. And that voltage, let's say 2.62, sorry, 7.5 minus 2.62 should be about 4 point something, 4.8-ish. Of that 4.8-ish volts, we have this zone right after the resistor will have the potential of about 4.8 volts. And we know that all of that is going to drop across the rest of the circuit to 0 before we get back to the battery. Now, things might look a little scary with this upper part here because of the number of resistors in it, but we're not looking at this upper part, we're looking here. And we got the 4.8-ish volts, your numbers will vary. That's going to split and drop across both branches at the same time. Because in a parallel circuit, the current splits, but the branches share a voltage drop. Because this whole zone before the branch split is the new reduced voltage, and this whole zone afterwards is 0. So the voltage drop from here to here is going to be that remaining reduced voltage. And since this is the only resistor on that branch, its voltage drop should be that new reduced total. So if we look at the answers presented on this teacher version, as soon as my mouse decides where it is. Yep. Using the result from part F and the battery's potential difference, what is the voltage drop across the 3 ohm? 4.8-ish. That's just the difference between part F and the original circuit voltage.
But like, why doesn't that voltage split within the branches?
Voltage doesn't split. Voltage is like water pressure. Current is the amount of electricity. Like there's a fixed amount of electrons moving, and when that hits a fork in the road, the individual electrons have to go one way or the other. So current will split that junction, but voltage is like water pressure. If you've got a hose with water pressure in it that splits at some point, the water pressure doesn't necessarily split, it's now just pumping through 2 hoses at once.
So you are going in with that 4.8 volts. Can you go back to the picture? Into both branches of the parallel.
Correct.
So 4.8 for the 3 and then 4.8 for the other parallel one on top.
Yes, and things will get a little weird in the top branch because of how many resistors there are, but that's not what the question asks. The question is just asking voltage drop on the 3.
Okay. I didn't know that.
And so with that answer, with part G, we're then asked for number H, what is the current in the 3 ohm resistor? We know the voltage drop across the 3 ohm resistor. We know the resistance of the 3 ohm resistor. V equals IR. Find out how much current we got, which should always be a smaller number than part E, the total circuit current.
Wait, why?
Because this total current splits before it reaches the 3 ohm. Some of it has to go down the other branch.
Okay, the current split, not the voltage.
Correct. Voltage doesn't split. Voltage drops when it hits a resistor.
Yeah,
And
because you're trying to go to 0.
the voltage does try to reduce to 0, yes. It can only drop across a resistor, and from here to here, it hasn't hit another resistor yet. And additionally, once we pass this resistor, there's no other resistors left. So this whole zone after the 3 and after the 4 is the area of 0 volts. Because there's no obstacles left before you get back to the battery.
So the 3 ohm resistor is doing the same effect that the top circuit is doing and trying to get 0, and getting 0?
Yes, both branches are trying to get to 0 volts, but this is the only member of its branch, so it's going to drop all the volts, whereas up here, it'll drop one piece at a time before hitting 0.
Okay.
Any other questions? So, these are due tonight. Because of the kind of specific nature of this long question and a couple of quiz questions as well, that kind of require you to go one step at a time. You have to get this right and then do the next thing. Please, please, please email me or come find me in my office as you are working them. If you are getting it wrong and you need the answer to be correct to move on, I will gladly step you through it. I will tell you if you're doing the right thing. I'll tell you if you're right and whether the sign is just being mean. Please do not hesitate. Because I've already gotten a question or two about things like that. And definitely do the homework first. Number 8 will help you with the quiz.
Like for the quiz, the B was harder than this one. I don't know why.
Well, the time trial nature of it is stressful. There's also, well, sometimes more parts is scary and tedious, but sometimes more parts is, more chances to get things right. If it's just one answer, all or nothing,
Yeah.
that gets my blood pressure up, which is why I have a sign and why I put in partial points myself retroactively. Okay. So please let me know as you are finishing these up tonight. And moving on, we're kind of skipping around the remaining electrical magnet chapters now to hit on what I feel are the most important things to know to exist as a human on planet Earth. And magnets, despite being weird and mimetically mysterious, are omnipresent and very important to our daily lives as humans. So we're going to be discussing those next, as indicated by lab this week. Now, magnets are a big old meme in that we don't always know why they work or why they do what they do. We are, however, able to measure them and do several calculations based on them and understand a lot of what they do. We just don't always know why or how. And we're going to focus mostly on the what the magnets do, and what that means for our daily lives as humans on planet Earth. Now, this is the third field force that we have discussed. This is not to be confused with a force field, although they're similar concepts. A field force the circular definition of a field force is a force exerted
In a field.
by a field, yes. So if something gives off a field, gravitational field, electrical field, magnetic field, it will exert field forces. That's the circular logic definition, though. I'd say the definition that doesn't double back in on itself like a snake biting its own tail is a force that can be exerted from a distance without contact. I imagine, like most children, you probably played with magnets at some point. And can you confirm for me that magnets don't have to be touching to either attract or repel? These are very weak magnets. They always do the thing. And you can say the same thing about this definition for gravity, because even when you're not touching the Earth, gravity exists. And electric fields, because even when you're not touching a cloud, you can still get struck by lightning. That's not a great example. Even when you're not touching something electrically charged, your hair can still stand on end. That's a better case. So, magnets exert a field. It is a magnetic field. It has a north and south pole instead of a plus and minus pole. We use different terms because they are different things. Electric fields and magnetic fields are separate phenomena produced by separate things. Charged particles that create electric fields don't create magnetic fields. Meanwhile, magnets don't make electric fields. They are separate things. They're related, they interact, but they are separate.
Okay, I have a weird question.
Yes?
Okay, so the Earth has a magnetic field.
Yes, it does. It's a very important one.
Okay, and then you have North and South Pole, right?
Correct?
So does that mean that North and South Pole has like a concentration of whatever, you know how like you make magnets and I'm not really sure, I feel like it's iron. Is it iron?
A lot of man-made magnets are iron-based.
Does that mean that North and South Pole have a lot of iron like in the ground or something? Or like what makes it magnetic?
That is a very good question, and it is not that there is a bunch of magnetic material at the two opposite ends of the Earth. That is a reasonable assumption to make, though. The funny thing is, like I said, magnets are a big mystery, and we don't always know why they do what they do. We just know what they do. Earth's magnetic field is one of those mysteries, because we aren't 100% certain why we have one. We know that some planets just do have magnetic fields, and the ones that do are the ones that are usually capable of having an atmosphere, on the grounds that a planet's magnetic field protects it from space. I said a minute ago that a field force is not the same as a force field, but in this particular case, Earth's magnetic field is basically a force field that is constantly deflecting radiation and debris from space from actually reaching Earth's surface and its atmosphere. And
Wait, so is a force field any force?
a force field, a field force is a force exerted at a distance by a field.
But the field can be any type of field, magnetic, electric, or...
Correct.
Okay.
That said, there's no such thing as repulsive gravity, so we can only really use electric or magnetic fields to repel things. At least to my knowledge, there's no repulsive gravity. I suppose that'd be anti-gravity. Let me know if you ever figure that out. So, here on planet Earth, we have the equator, we have the north and south geographic poles, like the spots where someone didn't explore and found like the total opposite ends of the Earth from one another, the axis of spin, probably. So Santa lives here, penguins live here, and Earth's magnetic field is produced as if there was a giant bar magnet inside of the planet tilted like this. This is a bit of an extreme exaggeration. It's a little more vertical than that, but I want to get the point across. The Earth's magnetic field is tilted. And whatever is inside the planet making it, we do have hypotheses, but we haven't dug down to the core to see because, you know, it's the core. Whatever is in there is creating this magnetic field. And counterintuitively, this is the south geographic pole, but the end of the bar magnet down there is actually magnetic north. Meanwhile, the end of the magnet near the geographical north pole is actually magnetic south. So not only are the poles backwards, they don't line up with the geographic poles, and they're moving.
What does that mean?
It means 100 years ago, compasses pointed north to a slightly different spot. This is part of the mysterious nature of Earth's magnetic field, because over history, we have recorded the fact that this bar magnet is slowly weeble-wobbling around.
Which way?
I think it used to be more north-south, and it's slowly drifting. I think at the moment, this pole is closer to Alaska than it is to the Arctic.
You think it'll be horizontal?
I don't think it does, I don't think it will go horizontal. However, it does randomly flip. We have yet to observe this directly in human history, but there is evidence to suggest that not only do the poles drift, but occasionally the polarity just swaps. And we can tell this by looking at the arrangement of magnetic particles in the sea floor, because their magnetic particles are aligned based on what the magnetic field was when that amount of crust came out of the Earth. And as that crust keeps extruding, we've noticed like opposite bands of north-south pointing magnetic particles every couple hundred millennia or so.
I don't get how a compass works.
A compass is just a magnetic needle that is designed to align to these magnetic field lines. And this map of those magnetic field lines might look kind of weird until you remember that all of the flat maps of the United States are technically squashed from the round globe. So they're straight on the globe, they're just weird on a flat surface. The lines do stretch, straight from the south up to, well, straight from the magnetic poles, north to south. And the compass is just a magnetic object that is designed to point one end towards magnetic north and one end towards magnetic south.
But don't we base like we live on the East Coast, but that says west. So like it's actually like, this is, 5 degrees west, 10 degrees. Is that based on the magnetic core?
No, I think that's degrees off from the magnetic axis.
But like that still shouldn't be west, that should be east then.
Okay, that's degrees. I'm not sure where this map came from. I apologize.
Or are we supposed to look at it like if we are the core and then you look at it?
I am not sure. That is erring into cartography questions, which I am not. I apologize for not having an answer to that one. So the running hypothesis for why Earth's magnetic core exists is because of molten hot metal inside of, if not the core, then the mantle of the Earth. And since magma's liquid, it keeps flowing. So moving molten material is making the field, and since it's moving, it occasionally flows differently.
Wait, what did you say? What's liquid?
Magma.
Okay.
The running hypothesis is there's something molten and iron in or around the core. It's flowing while molten hot and charged. It's creating a magnetic field. And since it is molten, its flow occasionally shifts, which explains the drift. I don't know if we have a good answer for the north-south flip-flop.
Wait, but does that mean that if you, okay, like, let's say you go out in the world, you have your compass, what's north, what's south according to that?
Compasses, like if you buy a compass, is calibrated such that the needle pointing towards this magnetic pole is labeled north.
Okay. Okay. And so does that mean that, let's say it flipped and then you whip out your compass again, is it going to say the exact opposite?
Yeah.
Okay.
That does not happen within recorded human history. We don't know when it'll happen again. I don't think it's happened within recorded human history. It's based entirely on geologic evidence. Now, again, we're not entirely sure why it's there. It behaves very strangely at times, but it's very, very useful because this is not to scale, but we do have a sun. Our sun keeps us warm, which is wonderful. However, the sun not only shoots light at Earth, it also shoots every frequency of radiation imaginable, including the kind that makes hulks. along with a bunch of charged space dust particles, plasma type stuff. And we don't really want all of that, because if you get too much of that, you end up being like Mercury, who's a scorched barren wasteland due to the solar wind. So, thing to note is charged particles and magnetic phenomena like light approaches the Earth from space, and when those objects, I'm using a proton because I know the math for protons off the top of my head. Say a proton was fired through space and it's about to hit our atmosphere. When this charged particle hits the magnetic field, it will be, at least partially, deflected, which has the effect of reducing the amount of radiation and space dust we get on planet Earth. And because of that reduction, the amount that does make it through the atmosphere is just the amount that we need. If our magnetic field was any stronger, if it deflected too much, we'd be freezing. If it didn't deflect enough, we would be a scorched hellscape. Yet another reason why the balance of all the variables on Earth is fine-tuned for everything to exist. Other planets are scary.
So how does the ozone tie in with magnetic field?
I don't think it does.
Then why do we say that our ozone layer protects us?
The ozone layer
Wait,
is
did we
like a
say
second.
that?
The ozone layer is a second layer of defense from thermal energy specifically. I'd say
If we didn't have the
we
ozone
need
layer-
both. We need both of them.
Okay.
They work together. But I don't think the ozone gas is affected by Earth's magnetic field. This is first line of defense. This is what's happening out in orbit, and the ozone handles what makes it through the magnetic field.
If we don't have the ozone, do we die?
Probably. At the very least, things get a lot more uncomfortable. Okay, Earth has a magnetic field. That magnetic field is very important. Now, typically, one type of field will only interact with the same type of field. Gravity only really interacts with gravity, electric only really interacts with electric, magnets normally only interact with other magnets. If you were to just, I'm going to draw a magnetic field real quick. And I've shown most of you this similar kind of picture and talked briefly about it in lab, if you've had that this week already. If the green lines represent a north-south magnetic field, these are magnetic field lines, and we just drop a proton in the middle of that field, and it's not moving, we just put it right there, hold it still and let it go, nothing will happen, not inherently, because the electric field of the proton is not guaranteed to interact with the magnetic field lines. However, they can interact under a very specific circumstance. And this formula here describes that particular circumstance. One sec. Excuse me. So, this is our first magnet formula. The variables contained within. This is magnetic force is equal to, this is, I'm going to roll the board up and add extra definitions.
Wait, how do we know that it's magnetic?
I'm telling you that in this formula, this is force exerted by a magnetic field on an electric charge. So this is the fringe case where a magnetic field does act on an electric particle. Under normal circumstances, that doesn't always happen. This is the circumstance where it does happen. So in order for a magnetic field to act on an electric charge, we need three things. First, we need a charge. Lowercase q is still charge measured in coulombs. B represents the magnetic field itself. So the official variable for magnetic field strength is B. I don't know why.
Is it measured?
Good question. Magnetic field is measured in units of, measured in Tesla. So magnet begins with an M, the variable is B, unit is T.
4 or 5.
Yep.
It could not be worse.
But we can measure the strength of a magnetic field. The units for that measurement are in Teslas. We can measure them. We can see what direction they're moving in. Even though we don't always know why they're being produced by any given object, we can at least tell that they're there and know how strong they are.
What is its unsimplified unit? Because if Q is in no, V is that velocity?
It is.
Is-
About that in a second. Based on this formula, the unsimplified unit would be Newton seconds per coulomb meter.
Wait, why is Coulomb? Oh, this is meters per second. Yes. That's equal to
1 Tesla. Not a very good unsimplified unit, I'd say. Doesn't really tell us much. But the variable is B, measured in Teslas. That's good to know. So in order for the field to exert a force on a charged particle, we need one last detail, and that is velocity. Use a different color ink for this one. This detail is important. Dang it, that was the last one. Oh my gosh. New world record. The B term stands for perpendicular velocity. In order for the magnetic field to exert a force on an electric charge, the charge has to be moving perpendicularly to the field lines. And if this is the magnetic field, there are only two axes that are perpendicular.
Wait, the charge is moving? Perpendicular?
Yes.
Yes? Okay.
I'm going with that because it's easier to picture, but technically speaking, the charge could stay put and the magnetic field could change perpendicularly to the charge, and that would produce the same effect. Like if you move the magnet away, that could do it too. But this is easier to picture for right now. So, if the magnetic field stays constant and this particle stays perfectly still, what will the magnetic force on this proton be?
Nothing. 0.
0. If you plug in 0 for B, you get a 0 outward force. If the proton moved this way or this way, would there be any force? No.
Wait, both?
Either direction. If the proton was moving in the x-axis, would there be any
Oh,
force
because
from
it's not
this?
perpendicular. No, yeah.
Correct, very good. The velocity has to be perpendicular to the direction of the field lines, which means in this situation, the proton would either need to be moving up or down, or along the z-axis. Because both of those axes are perpendicular to the x-axis. And in those situations, you do get some amount of force from the field on the particle. And that is the situation that happens for space debris hitting the Earth. Because if the field lines go from magnetic north to magnetic south, the way that I've drawn this picture, the field lines will be pointing up at that spot. Meanwhile, this charged particle is moving along the x-axis. So those are perpendicular, the field will exert a force on the proton. That said, the force isn't probably going to be in the direction you would first assume. At this spot, the field is pointing up, the proton's moving forward. What direction do you think the proton's going to get forced in?
Like a 45-degree angle.
No, it will be a perpendicular direction, but it's going to be in the one direction that's perpendicular to both of those axes. If the magnetic field is currently in the y and the proton is moving in the x, the force is going to point in the z. And there are rules for this, and we'll end on this for today. There are rules for figuring this out. They're called the right-hand rules on the grounds that you have to use your right hand to make it work. Your left hand gets it backwards. Well, right hand works for protons, left hand works for electrons. And since all of physics refuses to acknowledge the way that electrons move, we're going to use the right hand for right now. So, the rule goes, you point your fingers, the actual fingers, in the direction the particle is moving. So in this case, that way. You point the flat of your palm in the direction that the field points, kind of like you're blasting it out of your hand. So field is going up at this spot, so fingers that way, palm this way. And the force is going to point the direction of your thumb if you're holding it out like an L. So in this case, field positive y, velocity positive x, force will point the positive z. So in this scenario, proton is rushing towards planet and the field's going to ping it off that way.
Wait, so your thumb shows you where what?
The direction of the force.
Of the two, like,
When the particle enters the field and the velocity points this way and the field points this way, the force that the field exerts on the particle will point that way.
where did the particle go with it?
Well, yes, the force is going to cause it to accelerate in this direction. After that point, some additional weirdness happens, but that's a good place to call it for right now, because I don't want to hold you over before a nice long weekend. So, focus on the Chapter 17 stuff. I will be uploading magnets, notes, and the assignment soon, but they won't be due for, until at the very least,
The next.
probably. Next couple weeks might be a little compressed in terms of material, but when I talk about magnets, there'll be, I like to see a magnetism test, and then we'll talk a little bit about making sound towards the exam. So the test is coming up. Keep that on your radar. It'll be in the next week, couple of weeks.
Like 20-something, maybe?
Probably. Yeah, test might be this last week. I will let you know. It'll be one of these 2 weeks.
Oh my god, and then we have exams.
Well, I want to leave a week for light and sound, and then a week for review. That's my plan.
And then our exam is the Tuesday, no, yes, the Tuesday at like 8:30, because I think I have the work thing. Are we in E-block?
This is election, yes.
Tuesday, May 11th at 8:30.
Oof. May 11th? Oh, do we have class that week?
May 11th? I think those are just exams, because they end on Wednesday.
Test date will be officially announced shortly, just to let everyone know. Do have a good day. Focus on Chapter 17 stuff for tonight. Have a great weekend, please. Please sleep. You don't need it.